I was thinking what to talk about because recently I work a lot on vector addition systems, which are like essentially speaking the same as Petri nets. But I asked Pierre, and Pierre said, "Oh, it would be nice if you talk about your work on unambiguous systems." So that's why I decided to talk about unambiguous systems, which are titled Techniques for Unambiguous Systems. And so what's my plan? Essentially speaking, I would like to tell you two things, but plans like that. First, I will define unambiguity and say a few words why I think it makes sense to research it. Just a remark: if you have any questions at any time, disturb me. I will be happy to get questions. In particular, if something is unclear. Okay, so then I will tell you about equivalence of unambiguous finite automata, which is a classical result, and it's based on weighted automata, and I think it dates back to Schutzenberger in 60s. I'm not sure about this exact date, but it's classical, and it's based on linear algebra. I think it's a very nice construction. And then I would like to tell you about our recent result on equivalence of languages of vector addition systems, which I abbreviate as VASs. And this is our work with Piotrek Hoffman, published just a week ago on Concours this year. And this, it's actually about a technique which we call look-ahead technique. I hope it may be also useful in other cases. And then I will tell you about connections to other of this kind of things. So unambiguity, some kind of multiplicity equivalence problem to other fields of mathematics, which even so far away as complex analysis. And I will just say a few words, but I think it's very interesting to me, these connections. So that's my plan. So essentially speaking, two things. One and second one. But first, let's define the notions. So maybe I should. It's a weird place where I stay, but maybe it's fine. Okay. So what is an unambiguous system? So we say that the system like finite automaton or automaton with something is unambiguous if for each word there's at most one accepting run. Yes. So for some words there can be many runs. If no run is accepting, then a word is not accepting. But if but there may be that one run is accepting and then word is accepted. But it's not possible that more than one run is accepting. Okay. So that's some definition. Why it's interesting? I think there are two, maybe three reasons. First one is that it's so. Of course, every deterministic system is unambiguous. Yes. If there is just only one run, it can be accepting or not. And so unambiguous systems are more, it's a more relaxed notion than determinism. But it turns out, but it's more strict than just no restriction on non-determinism. So it's some restriction on non-determinism. But it turns out that many problems become simpler in the unambiguous case. Related to the no assumption case. Simpler, I mean that computational complexity drops much. They become much more tractable for some reason. And it's not yet clear for me what's the reason, what's philosophical reason behind that. And I think this is a third reason why people study this, that it seems to be mathematically interesting to study these unambiguous systems. I think there are some connections, there are some connections to other natural notions. And I think this is also a reason why people study. And recently there is maybe not a lot of research, maybe it's too much to say, but there is more research on unambiguous systems. Okay, so that's about the unambiguity. With simplicity, so I claim many problems become simpler. I would like to give you at least a few examples what becomes simpler. So first of all, universality of, this is how I denote unambiguous finite automata, UFA. So universality for UFA. So if you ask universality problem for finite automata, this is p-space complete. But if you ask this for an ambiguous finite automata, this is known to be in p-time, actually even lower. I think NC1. I'm not sure. Moreover, equivalence problem for unambiguous finite automata, which is more general than universality, then it's also in p-time versus p-space completeness with no assumption. Another example is unambiguous register automata. So there is a very nice work from, I think, last year by Mikołaj Bajenczyk, Bartek Klin, and Joshua Merman on register automata, and they have shown that equivalence of register automata in the unambiguous case, they have shown something more general, but consequence of what they have shown is that it's in exponential time versus undecidable. So the problem of equivalence of two register automata is undecidable. I mean language equivalence. So maybe I haven't specified it. Yeah. So that's here. I mean language equivalence. And this is what we have shown with Piotrek Hoffman recently, but just a choice, there are more results, of course. But if you look at vector addition systems, in the unambiguous case, then language equivalence, one more time, is decidable, in particular in Ackermann, versus undecidable without this assumption. So just a few examples.
You cite these gaps for inclusion?
Could you repeat?
Well, instead of the equivalent language equivalence, language inclusion. So
yeah, I think I can say. So here we definitely have shown it for inclusion. Here I'm not sure. But yeah, I think most of this equivalence can be changed even to inclusion. Yes. Yeah. Okay. So let's go to the first result, which I promised you. So equivalence of finite automata in the unambiguous case. So the big plan is like that. I will do it via reduction to weighted automata, and I will also introduce weighted automata. I'm not sure how much you are familiar with weighted automata, but it will be quick in the case if you know it. So it would be by reduction to weighted automata and actually to a zeroness problem for weighted automata. And then I will show that it's reducible to the zeroness problem. I will define it, of course. And I will show you how to solve the zeroness problem. And the core of the problem is here. Here we will use linear algebra.
I have a stupid question. I know what universality or equivalence for deterministic automata. Or I know for what it is for non-deterministic automata, because they are syntactic notions. But this is a semantic notion. When they give you an automaton, you don't know if it's unambiguous. Or do you?
Yeah, so I assume...
Stance of your problem.
Yeah, so I assume I'm just given, I'm just promised that this is unambiguous.
And it's just finite state automata, like the usual automata.
This is this F, so it's finite automata.
Yeah, so how I imagine this, I haven't thought about maybe formalities, but I just assume that my input is unambiguous automata.
You get two non-deterministic automata,
which happen to be unambiguous.
And someone comes.
By the way, it's pretty easy to actually check whether automaton is unambiguous, because you may construct for finite automaton A, let's say you can construct finite automaton and A prime, which accepts exactly those words, which have more than two runs in automaton A. So if automaton A is unambiguous, then A prime should have an empty language. You just guess, some two runs.
It's polynomial.
Well, it's polynomial. I think it's polynomial. Yeah, because you just guess two runs. It's a regression. But you can pretty easily check whether your automaton is unambiguous. Okay. Okay, so here we will use some linear algebra. In the plane, I noticed that my talk may have some similarities to talk by Jurek on Friday. I will also tell something about multiset semantics and about linear algebra, but I don't know how much. Okay, so that's the plan for this part. So what are weighted automata? I will consider actually plus times weighted automata, yeah? Over semiric plus times, if you know this. So this is, I will define it on example. So this is an example of weighted automaton. You have state, you have transitions. Each transition is labeled by a letter, you know this, and by a weight. Here we have weight 1, here we have weight 2. And additionally, each state has an input weight. In this case, this state has input weight 3, this state has input weight 0. I don't draw an arrow with 0 label there, but you can imagine it's there. And each state has an output weight. This state Q has an output weight 1, and this state has output weight 0. Okay? And what is a weight? Now I have to say what is a weight of a word. What is the weight of a run first? Weight of a run is product of weight of all the transitions on this run. And also of the weights of, say, input and output transition. So if you have a run, let's say you come here, you start here, you go via B here, and you go out here, then this run has weight 3 times 1 times 1. It's 3. Okay? Hope it's clear. And what is a weight of a word? You sum up weights of all runs over this word. Okay? So let's look at an example. What is a weight? This is how I denote a weight of such a word. So actually, you can see that this is you can think it. So if you forget about weights, it's an ambiguous automaton. So there is just one way to start here and to end here. You need to first be here, then so first loop here, then take this transition on the last B, and then do the suffix of ace here. Yes. So actually, you have only one run which starts here and ends here. So over this word, you need to jump from state P to Q on this B, and then loop here. So there is just one run. It enters here with weight 3, then it loops here, then it goes here, and then the last 3 A's, it takes these transitions. And then it goes here. So its weight is 3 times 1 times 1 times 1 times 2 power 3 times 1. So it's not 12, as I wrote. It's 24. Yeah. Is it clear? Okay. Okay, so this is weighted automata. So now I will tell you how to reduce equivalence problem for UFA to unambiguous to equivalence problem for weighted automata. Let's maybe say when two weighted automata are equivalent, we say that two weighted automata are equivalent if for each word, the total weight of a word with respect to the first automaton is the same, is equal to the weight of a word with respect to the second automaton. Okay? So I claim that I can, if I have two UFA, A and B, I can very easily transform A to A prime, B to B prime, such that A prime and B prime are weighted automata, such that these two have equal languages, and if and only if these two are equivalent. How do I do it? I just write weight 1 on each transition. But let me show that, that this is indeed fine. So each transition has weight 1. What about input weights? Input weights of initial states are 1 and of non-initial are 0. And output weights of final states are 1 and of non-final are 0. So let's now look at, just for each run. So even without assumption on unambiguity, just each run has weight 1. So what is a weight of a word? It's number of accepting runs for this word. But here, these two automata are unambiguous. So for each word, it has weight 1 if it's accepted. It has weight 0 if it's not accepted. So clearly, I guess that you see this equivalence. Yes. You just count accepting runs, and in the case of an ambiguous system, it's either 0 or 1. Okay, so we have reduced our problem to the problem of equivalence of weighted automata. By the way, actually with weights only 1, but let's not focus too much on that. So what is a zeroness problem? Okay, so maybe let me first say, tell you what is a zeroness problem for weighted automaton. You ask, is it true that for this weighted automaton, each input word has a weight 0? So it's a question, is the function computed, let's say, by this weighted automaton equally 0, constant 0? This is zeroness. So let's observe that A and B, A prime and B prime, are equivalent if and only if the following function, like for each word, A prime of W, by this I denote, the weight of W with respect to A prime, minus B prime of W is constantly 0. They have to be equal all the time. So now the point is that I can construct such a weighted automaton C, which for each word computes A prime of W minus B prime of W. How do I do it? I just take A prime, I take B prime, and for B prime, I swap input weights from 1 to -1, or from any x to -x. And in that way, I have total sum of runs as A prime plus minus B prime. I hope it's clear, yeah? So now, if I take such something like that, I just have to check whether C is constantly 0. So I have to check zeroness for C. Yeah, I hope you agree. So it's enough to be able to check zeroness for weighted automata in order to decide language equivalence for unambiguous finite automata. Now I would like to mention something. So there is another problem which I think is very interesting. It's called, you can call it multiplicity equivalence. So what does it ask? For finite automata, it asks, so we say that two automata, A and B, are equivalent if for each word, number of accepting runs over this word in A is the same as number of accepting runs in B over this word. So it's a bit, it's finer than language equivalence, yes? For unambiguous automata, for each word either you have 0 or 1 run, so multiplicity equivalence is the same as language equivalence. But for non-deterministic automata, it's more detailed. And actually observe that this reduction, which I have shown you, it works exactly for multiplicity equivalence. So what we will actually show to be in p-time is not only language equivalence for unambiguous finite automata, we will actually show that multiplicity equivalence for finite automata, for non-deterministic finite automata, is decidable in p-time. Yes, because this A prime and B prime, what do they output for a word? They output number of accepting runs. So this is constantly 0 if and only if A and B, the original finite automata, were multiplicity equivalent. Okay. So now, how to solve this zeroness? So I jump into first technical part. I have 3 more technical slides, so please disturb me if something is unclear. For students, you may devote 1 lecture for this or half a lecture, but I would like to make it a bit faster. So let's fix a weighted automaton A with n states. Okay. So now, if you have a word W for any word, you can associate a vector, which I will denote vec of W, with this word. It's so what is this vector? You start so for each state, you keep an entry of this vector. So here is why you have dimension n, and for each vector. Yeah, for each state, you have an arbitrary entry, and in this entry, you have a total weight of all the runs over this word W. Yeah? You start in all the states, you sum up all the runs over W, and you look at all the runs which end in state Q1. And you look at the total weight of all these runs, and you put this into first entry of your vector. You look at the total weight of all the runs over our word W, which go to state Q2, and you put this value into second entry of our vector, and so on. Is this clear? This is crucial if there are some questions. Yeah? So here you have.
Each time you start from the initial state, and then the parameters of this vector coordinates depend on the state where you finish.
Yeah, I mean, so here you have entries. So for each state, I have one entry.
Yeah.
So I start. I mean, so if we are in weighted automata, in some sense, all our states are initial. But this one is initial with weight 1. This one is initial with weight 5. This one is initial with weight 0. So it's actually not initial. So you somehow already at the very beginning you have a vector. Let's say. Yeah. Okay. So now I will define a vector space, let's say over rationals. This is a key trick. So let k be a number, and we will consider words of length up to k. And I will define a vector space, a linear space, vk, to be what? To be these vectors for words which have length up to k. And additionally, I will use these vectors as generators of this space. I will consider vk to be space spanned by these vectors over rationals. Okay, so it's not only set of these vectors. This is a trick, but we make this because natural move would be maybe let's consider all the vectors which can be achieved by short words up to length k. The trick is to make this set more round and make a linear space out of that.
When you say span by vectors, you mean like
generated
generated by the additions of all the multiplications?
Yeah. So I mean, I take these vectors as generated. I take finite sums of these vectors with rational coefficients. Okay. So now I have that's a nice trick, I think, to consider these vector spaces. Yeah. So you can see that vk with k bigger, it may grow or may stabilize. Yeah, because we consider more and more vectors, always up to length. Okay. So now, yeah, this is kind of a definition of out function. So you have these output weights. These output weights for each state, you have output weight. Yeah. So observe that weight of a word is actually you first go through this word and get this vector, and then you have this vector for each state. You have a total sum of weights somehow accumulated in this state, and now you apply to this vector, the output weights for each. You sum up for each state current weight times the output weight of this state plus weight accumulated in state 1 times output weight of state 1 plus weight accumulated in state 2 times output weight of state 2 plus, and etc. So this out is a function taking n arguments and outputting one argument. Do you agree with that? Yeah, I mean, that's, I hope, yeah. Out. Is it clear what out means? So now the key observation is now, so this is, I think, the most hard thing, but I will read it for you slowly and I will prove it. So I claim that this weighted automaton fulfills zeroness. I mean, it's constantly zero. If and only if we have the following, the following property. All vk subspaces are included in the kernel of this out function. So I should maybe say this in better words. So if you take the out function and apply it to vk, it only goes to 0. This is how you should read this. You apply out function to anything in vk, it should go to 0. So how to prove this equivalence? So first of all, if this is true, that if you apply out function to anything in any vk and it goes to 0, then in particular, applied to any vector of word v it goes to 0. So automaton A is 0. So right to left is clear, I hope. And why actually, if automaton A is 0, then any vector, when any weight of W is 0, so function out applied to vectors of W, it goes to 0. But here we have VK, not only vectors, but VK, they are generated by these vectors V. So they are spanned by this. So if output function applied to vector of V is 0, then also the combination of vectors is also have to go to 0. So from left to right, you use the fact that this VK is a linear space, and that this out function is a linear function. I hope you see this. Any questions at this point? I think this is the most complicated.
Is there anything you have done so far that doesn't work for an arbitrary semi-ring?
Oh, I haven't thought about this, but for Max Plus,
I think not, but I'm not sure.
good question. But well, we can think on during the break. I'm not sure about. So this is based on linear things, yeah. Max Plus. I would be suspicious, but maybe. Okay. So let's go further. So in order to check whether A is 0, it's enough to compute this VK, okay, for any K, but you will see that we have apparently many options, and apply, the out function and check whether this goes to 0. So it's enough to compute this VK. This is just copied from previous slide. And now let's observe. So how these VKs, how do they behave? What is V0? V0 is spanned by vector of empty word, yeah? This is just simple vector. For each state, you take the input weight of this state. You make a vector out of this input weight, and you make a linear space out of it, so it's just a line. And then, if you get more, if you look at longer words, this VK may grow or may stabilize. So we will make a trick of compute. I will maybe not show you, but hand wave you how to compute VK plus 1 from VK. You can already kind of see it. You can obtain some vectors, and then you make one transition more. So I claim that VK plus 1 is generated by or spanned by what? You take generators of VK and you apply transitions over, let's say you have letters A, B, C. So you take generator of every generator of VK and you apply A transition to it, you have some new vector, B transition to it, and C transition to it. So you have 3 new vectors. And for each generator, you do this, and you have new generators. And additionally, you have to take into account all generators, for shorter words, because VK plus 1, it subsumes VK. So I claim that VK plus 1 is generated like that from VK. And this is technical part, but believe me, these generators, they don't get, the numbers in generators may grow, but they don't grow too fast. I don't want to focus on that. So this is how we compute VK plus 1 from VK. So how to decide this? So this is just recalling. V0 is spanned by this vector. And observe VK plus 1 is a linear space which contains VK. So either it got bigger, but in the case it got bigger, dimension is bigger. Yes. Or it didn't get bigger, so it's the same. But we have, here is the key point. So either it stays the same, or if it grows, it cannot grow just a little bit. Dimension have to grow. So it means, but all these VK, they are included in the Z power n in n-dimensional space, where n is the number of states in our weighted automaton. So this means that VK grow. At some point it stabilizes from VK plus 1 equals VK. So dimension didn't grow, and this point is pretty quick, after at most n steps. And if VK plus 1 equals VK, it has to be equal also VK plus 2, VK plus 3, and so on, because the step from VK to VK plus 1 is the same step as you do from VK plus 1 to VK plus 2. You can think it's multiplying by matrices, but just applying this these letters, yes? So the algorithm is you just compute VK under stabilization, which is very quick. And you have this final VK, V stabilized, and you just check whether it's included in kernel of the output function. So here you can actually see that if something, so if, for example, if these two weighted automata are different, they are not equivalent, you have also a pretty short word of length up to n, which differentiates them. So the same for example, for unambiguous finite automata. If languages differ, they differ on some short word. By the way, yeah. So here, yeah. So therefore, it's in p time. I have to show you maybe that each step is in p time as well, but I hope you believe me. So I like this very much, this trick, and it's definitely general. Okay.
Equivalence of probabilistic automata is also in p time. Is it the same argument? Might be, right? Because
might be.
The semi-ring, right? You have it for the probabilistic semi-ring.
I would guess so. Probabilistic automata, they are weighted automata, you might say. Yeah, simply. Okay.
I'm not sure we have to go to vector space and take this plan. Is it because at some point we do simplification of this?
Yeah, so where's exactly? So where is the trick? So the trick is that if you make it rounder, so if you make it a vector space, if it grows significantly, so dimension grows. If you wouldn't do it, I mean, I can't argue that you have to do it. Maybe you have some other trick to do it, but otherwise, you know, maybe set of vectors reached by words of length k plus 1, they are just a bit bigger than words of length k, and you have to work with these details, you know. That's the point. Okay, so let's go to vector addition systems, to my second part of the talk. So I will actually talk about vector addition systems with states. I will first briefly introduce what is this. I will abbreviate this as VAS. So a VAS is just a finite automaton with a bunch of counters. In this example, you have 3 counters, and each transition can modify these counters. So for example, this transition, it adds 2 to first counter, it decreases second counter by 1, and it doesn't touch the third counter. Okay. And what is important, counters cannot go below 0. They are always non-negative integers, and you don't have 0 tests. So you can, if second counter is 0, you just cannot perform this transition, you know. Okay. And of course, if we consider languages, then each transition is also labeled by a letter from some finite alphabet, or maybe epsilon. So here is an example of a run. So you may start in state P, and this vector valuation, you may, for example, apply this transition. So when you decrease first counter, increase second counter, and then don't touch third counter. You may apply this transition one more time. You may go to state Q, don't change counters. Well, and so on. I guess this is clear. I hope so. Yeah. I have to mention this model of VASes or VASes with states. It's essentially equivalent with Petri nets. So if you know Petri nets, you haven't heard about VASes. This is essentially speaking the same, a bit different phrasing. Okay. Okay. So now, what is a language of a VAS? How do I define it? So yeah, VAS one more time is this vector addition system with states. I have to say how do we start and how do we end? We start in initial configuration. I call configuration a state together with counter values. Okay, this is a configuration for me. And how do you accept? I propose, so here I consider acceptance by states. You have a bunch of accepting states. You may define it differently. You may define acceptance by final configuration. You know, let's say state P with counter value 0. Then this is more complicated language. Yeah? Or set of finitely many configurations. Here I define acceptance by states. Then it's a simpler.
It's the same as a closed set. No?
That's the same. So it's coverability style. And I define a VAS, I say that a VAS is deterministic if each reachable configuration is deterministic. You have no choice. So you may imagine a different definition that, if you look at the automaton, then there are no two outgoing edges labeled by the same. Here is a bit, but there may be automaton state in which it has two options, outgoing edges labeled by A, but in each reachable configuration, one is impossible. So this is how I define deterministic VAS, but it's not very important. So now what about language equivalence for VASes? What do we know? So first of all, in general, it's undecidable. It's undecidable either for dimension 2. I'm not sure about dimension 1. I should probably know it. I guess it's known, but I forgot it. I don't know. But in general, it's undecidable. For deterministic VASes, this is decidable. I think it was known. Actually, recently we have shown, in this paper, we have shown as a simple observation that it's actually Ackermann complete. So the same as reachability problem. So the natural question arises, what for unambiguous systems? Is it decidable or not? And we have shown that it's actually decidable and Ackermann complete. But I think this is more interesting. This is we have shown this with Piotrek Hoffman, on Concours this year. Okay, so how do you start approaching this? So maybe I haven't said it, but at the beginning I have shown you this another result for unambiguous register automata, which I told by Bojanczyk, McLean, and Merman. This was also by an approach of, let's say, going into vector spaces. So a natural question would be, okay, so let's try to define a vector space. Now it will be more complicated because you don't have finitely many states, you have many configurations, reachable by VAS, and try to define some kind of vector space out of that. And try to define zeroness for weighted automata with counters, kind of weighted VASes. But this will not work because we can ask, okay, natural approach would be try to reduce to zeroness and then solve zeroness. But the question is zeroness decidable? If zeroness would be decidable, it would actually imply that multiplicity equivalence is decidable for VASes. As I shown you at the beginning, imagine this finite automata. Multiplicity equivalence, you remember, for each word you have the same number of runs, can be reduced to the zeroness. So if we would solve zeroness for weighted VASes, whatever this is, we would have multiplicity equivalence also decidable. But it's known to be undecidable for VASes by a beautiful paper, I think, by Petri Jančar in 2001, who shows that, essentially speaking, every reasonable equivalence, which is finer than language equivalence, is undecidable for VASes or for Petri nets, whatever, how you prefer to call them. So we need to choose different approach. And you may think, okay, that's probably undecidable, but that's not true. It's decidable. And our approach is we reduce it to deterministic case. And I hope maybe this can be of broader interest. Maybe unambiguous systems, maybe in some more generality reduced to deterministic systems. I don't know. So what's the idea? So the idea is that if we have an unambiguous VAS, two unambiguous VASes, we add some information to them to make them deterministic. And this information will be in each, if you have a word, we will consider actually some kind of extended words, words such that in each letter you have more information. And on a word, for a letter, you add some information about the suffix of this word. I will tell you details in a moment. So it's a look-ahead style thing. if Automaton goes for it, on a letter it reads some information about a future. It has some kind of look ahead embedded into the word. So more concretely speaking, the information added will be, does the suffix from this point belong to some regular languages, to a fixed set of regular languages of our interest. It's about suffix. And it will help Automaton not to guess some future, but it will have some knowledge about future, so it will be forced to choose deterministically some direction. And this is, so now we jump a bit into technicalities. This is best captured by monoid. So you can imagine I have some bits, for each of these regular languages, I have some bits in which state Automaton is, but this will be ugly. So we capture it by monoid. I'm not sure how much, what's your background? Are you familiar with monoids? So I will just mention very briefly that monoids are a very convenient approach to regular languages. So we consider homomorphisms from alphabet star, from words to finite monoids. And such a homomorphism can very conveniently recognize regular language, and there is a known theorem that for each regular language, L, with just, like a recap, for each regular language over finite alphabet sigma, you can find easily a homomorphism from word to finite monoid, and some subset of this monoid, F, like think about final, the good elements of a monoid, such that your language is exactly this set of words which is mapped into a good elements of monoid. Yeah, so your language is inverse image of these good elements. You have, you can, instead of Automaton, and your words are these ones which are mapped into good states of Automaton, you have a monoid, and your good words are mapped to good states or good elements of monoid. Okay, so how the reduction works? I have a few slides here. Yeah. So let's have this homomorphism. And for any homomorphism, I will define something which is a map, depends on the homomorphism. So what does it take? It takes a word over sigma, and it changes into a word over sigma times monoid. So each letter is extended by a monoid element. And additionally, you add one letter at the beginning. So how do you exactly do this? Imagine you have a three-letter word. So an image of this word is a four-letter word. Here we have first letter and then three next letters. And at each letter, let's say A, you add as a second element H of the suffix of BC. Okay? So this is information about the suffix, where it's mapped. Here in B, it's H of C. And here you add additional, for technical reasons, additional letter, which is like empty thing, and image of the whole word. So for each homomorphism, we just define something as map H. Okay? So now observe, so I have two claims. First one, this is actually very easy. For each homomorphism, like that, the following holds. You have two languages, K and L. K is included in L, if and only if map of K is included in map of L. This is just because this map is a function from words to words. So, if K is included in L, then image of K have to be included in image of L. On the other hand, this function is injective. It cannot glue to words. So if image of K is included in image of L, because if it's injective, K is included in L. So our trick will be, we will, instead of checking thus inclusion, we will check inclusion of these maps, and for smartly chosen H, we will be able to phrase it in deterministic thus way. That's the point. And here comes the second thing. For each homomorphism and each thus, V, we can construct another thus, VH, which accepts this language map of language of original VAS. Okay, this I claim. I will prove it on the next slide. And the main point here is that if our goal is the following, if I choose H such that VH, so we are actually, dealing here with two VASes, yeah, like V1 and V2, such that both V1H and V2H are deterministic, then instead of checking inclusion of these initial VASes, I can check this inclusion of these VASes, and they are deterministic. So I will be able to check inclusion there. Okay, so here I maybe confused you a bit because I'm talking about equivalence and I'm checking inclusion. Actually, inclusion is also decidable for deterministic VASes. Maybe it's better. I should maybe phrase it in inclusion method. So that's the approach. So now what should I show you? I should show you that indeed for each homomorphism and a VAS, I can compute this VAS, VH, and I have to show you that for particular chosen H, I have deterministic thing. Okay, I worry I will prolong I will not finish in 2 minutes, but I hope it's fine. So the reduction is, so I will maybe quickly go through that because this is not the most interesting thing. So for a VAS, I can construct this VAS VH. So what are states? The states are as previously Q, and each state, it remembers also a monoid element. It's a natural thing. If you add monoid elements to your words, to your letters, states of VAS should also remember this. And you have additional some initial state init with $. So initial state is this init with $, and final states are final states of the VAS, the one which accepts language, and the monoid part should, say there is nothing in the future. So H of epsilon. And for a transition, if we have such a transition in a VAS, how do we extend it to a new VAS? We create, if we have this state with some monoid element M, you read a letter A and M prime monoid, it means that in the future you have M prime. So you go to a monoid state Q, to VAS state Q with monoid element M prime. So this second part, it means all the words starting here, they should have monoid element M prime. Yeah. So this is exactly this. This is why this M prime should match this one. This says in the future I have an M prime, so I jump to a state with future being M prime. And here I also have to check consistency, that this M and this M prime, they fit together. So A homomorphic image of A times M prime should be M. M is A or H of A times M prime, or some border case, initial state case. I will not dig into that. Now about separability. I have to mention you briefly separability because this is our tool. So we say that two languages, GandALF, are regular separable. So as this. If there is some regular language S, which is like here, so K is included in this S, and L is disjoint from this S. And a few years ago, we have proven with a bunch of colleagues the following thing, that each two disjoint VAS languages with acceptance by state, this is important, are actually regular separable, always, if you assume disjointness. So in particular, if you have a language accepted by VAS and complement is also accepted by VAS, then it's regular. I think it's interesting. And we use this approach to our setting. So actually, we have been able to extend this. I mean, we have been forced to slightly extend this theorem in our setting. So I will read this. For each VAS, there is a finite family of regular languages, this family F, such that if you have two languages, language of C1 and language of C2, or I denote by language of C1, I denote language of words accepted if you start in C1, if your initial configuration is C1. So if you have L of C1 and L of C2 are disjoint, so nothing is, they are disjoint. So by the previous slide, we know that there is a regular language which separates them. And here I claim that for a vase, you can choose a finite family of separators, such that if LC1 and LC2 are disjoint, then they are separable by some language from this family. You have just a finite family of candidates for separators. Okay, so if you have this, then I claim that for each unambiguous vase and the homomorphism, such that this homomorphism it recognizes all these languages from this family, this is important. Then, if I compute this VH, this is not exactly a vase, this is something almost like a vase. I will tell you a detail there. Then I claim this is deterministic and computable. So this is my last claim, but actually by choosing this homomorphism, I will have this my VH deterministic. And why is that? So then equivalence is decidable for unambiguous vases. Yeah, you see. So this is the end of the thing. We reduce to this case, and I claim this is deterministic. So the only thing I have to show you is why this is deterministic. And this is one slide thing, one slide just. So this is just claim copied here. So imagine it's not deterministic. So you have some reachable configuration here, and here you have two transitions over letter A and monoid element M, and here the same, going to some configuration C1 of M and C2 of M. So now I claim that if L of C1 and L of C2 are both non-empty, then they intersect. This is not trivial. Let me argue why. So assume that L of C1 and L of C2, they are both non-empty. So here we have some run, and here we have some run, which accepts here and accepts here. So assume that they don't intersect for contradiction. If they don't intersect, it means by our separability lemma that they are regular separable. Yes, because they are disjoint. L of C1 and L of C2, they are separable, moreover, by some regular language from our family. Yes. But here, if they are separable by some regular language from our family, this should be visible in the monoid, yes? Because then L of C1, everything in the future here, I mean, so there should be some regular language like distinguishing future of C1 from future of C2. And here we claim that there is some future which has exactly M, and here is some future which has exactly M. So we cannot separate future with monoid M from future of monoid M by language from our family. This is impossible. I hope, yeah, I can go into details on a break if this is unclear. But this means that if they are both non-empty, then they intersect. And this means here is some future, and here is some future, which is the same. This is contradiction with unambiguity. You have two runs, here, here, and here, here. This contradicts unambiguity, and this is the end of a proof. So here I should say about this, why this is not a vase exactly. Here I say if they are both non-empty. But if one is empty, then it's okay. So I have to exclude configurations with empty language. So from my vase, I have to cut off some parts like empty language and below. And actually, equivalence is also decidable for deterministic such vases with holes. Let's say we have shown it, but this is like a technical detail. I wanted to give you an overview. You see, there are some details, technical, but this is an overview. Okay, so VH is deterministic after removing all this. So this finishes the proof. Just one, okay. Now a slide about multiplicity equivalence. So I think this is very interesting. So this is like multi-set semantics for automata, which Jurek will probably tell about more in database setting. So for finite automata is in P-time. For context-free grammars, decidability is a big open problem. For context-free grammars, language equivalence is undecidable. There is a conjecture where multiplicity equivalence is decidable. So maybe this is somehow a better semantics. Maybe this is a better point of view and better, more tractable way of looking into systems. That's a question, I don't know, but maybe we should look at multi-set semantics on Automata. Another interesting point for integer vases over one letter, there was recently an interesting paper which shown that in this case, whatever this is, multiplicity equivalence is decidable, and a technique was holonomic sequences, so some kind of fancy recurrence sequences. And we also recently worked on one integer counter, and we have found some connections to complex analytics, which never happens in our, I mean, I haven't seen this. So I think this is interesting. This has connections to deeper mathematical notions. That's why I think it's worth study. So last slide, future work. I think big question is philosophical questions. What makes an ambiguous system actually easier? Not really weighted automata, because in some cases you can do it, as in vases, and it's not because of going into vector spaces. Maybe something else. Is the look-ahead trick more universal? I don't know. Maybe it can be applied somewhere else. I think that maybe there are some more connections between unambiguity and separability. So here in this, I have shown you how separability may help unambiguity, maybe also in different cases. And I think exploring multiplicity equivalence is a very promising question. Thank you very much. Sorry for prolonging a bit.
Thank you, Wojtek. Maybe let's take one or two questions and then go on the coffee break, unless everybody wants to go on the coffee break.
What is known about the expressivity of deterministic bases and ambiguous bases and general bases?
I think this is a missing piece. Maybe it's too easy to do such that I guess they are probably all different, but I don't know any work which have lemmas like that. So the question they could be is all equal. I think that I haven't seen a theorem that they are all equal. Deterministic are definitely. Deterministic should be easier than non-deterministic because a bunch of problems is decidable here. And I think this is known that deterministic are not as expressive as non-deterministic. I think unambiguous are in between, but I don't have a theorem.
You have a question? No? Okay. I have one. So in the transducer world, they look at k-valued things. So is this interesting, this k-ambiguous case, where instead of at most one, you have at most k runs? So
I think it is, but I think that unambiguous is more natural. So actually our work on vases, we have actually shown it for k-ambiguous vases, for finite k, but I think that the model for just unambiguous is more robust, but it's also interesting.